n plus m quantity squared. Okay, that's both, and both of those are factorization. And then guys, what do we know about the variables n plus m? What do they simplify into?
K squared.
Yeah, some variable squared, some integer squared, excuse me, okay? We can call it k or p or whatever you want, okay? I'll just say k by closure. K is in it. So this is by closure. Okay. And I want you guys to notice that nothing up there is above algebra 2. Okay, nothing's too sneaky. The factorization might be a little tricky because we don't factor trinomials that have two variables in them all the time. But hopefully you guys can see how that works. Okay. So guys, isn't it valid to say that by above, this is going to be equal to k squared, which is a perfect square by definition of perfect square. I'm going to write it over here just because I ran out of room. So we're going to say, for step 3 if you would, thus, a plus 2 roots of ab plus b is equal to k squared, which is a perfect square by the very definition. We can just say by definition of perfect square. Alright, so let me give you guys a moment to copy that down, okay, and then we're going to go ahead and start on rational stuff. Everybody good with this, guys? Any questions I can answer about the process that we're going to utilize to be able to go through and illustrate how this direct proof is going to work just for integers, right? Now we haven't gotten to rationals, radicals, floors, and ceilings and all that yet. Okay, we will. Okay. So guys, let's briefly take a look at the definition of rational numbers and maybe be able to show a few things rational, and then next time we'll probably get to the proofs of this stuff. Okay, so, John?
Yeah, so basically what you're doing, like two things, you're finding the well not just two things, but I mean, you're finding like the definition of something, like an odd number, or just whatever it says, odd, even, or a perfect square, maybe that, and then you just plug that into the equation that's in the problem.
And then you just do your algebra from there. I think you said it pretty nicely.
Yeah.
Okay? So you use your definitions, even, odd, perfect square, whatever it might be. Then you plug it into the original problem, and then from there it's just algebra stuff. Okay? Good way to think about it. Okay. Other questions, guys? All right. So a rational number. Okay. If a and b are integers, a rational number is the quotient of two integers. Okay, so r can be written as a over b, and a and b share no common factors. Okay, so basically that just means it's in lowest terms. Okay, I can show that 37 very easily is rational, right? So how can I write 37 as a rational number?
37 over 1.
37 over 1. In fact, couldn't I just put any integer over 1 and show it's rational? Okay, so 37 is 37 over 1, which means that it's rational. Okay? Easy enough, right guys? We wish the entire exam was that question. Okay? 0.83 repeating is rational. We just have to show it's rational. Okay? And maybe some of you guys have seen the trick with being able to show that a repeating number is rational without using a geometric series. Okay? I know some of us could do it with a geometric series, but not all of us have suffered through Calc 2 yet. Okay? So did anyone remember, or has anybody seen the trick where you can show that a rational number that a repeating decimal is rational? That's okay. What I'm going to do is, this is for part 2 of this. Okay? So let's let x be equal to 0.83, 83, 83, 83 repeating. And because there's two values, or two decimal places that keep repeating, what I'm going to do is multiply it by 100, okay? Because that would move the decimal point 2 places to the right. So, this implies that 100x, and again, because only two digits are repeating, I would say 100, If it was 3 digits, it would be 1,000. If it was 4 digits, it would be 10,000. Okay? Guys, isn't it true that 100x is equal to 83.838383 forever? So nobody doubts that, right, guys? I mean, if I just define those as variables or even strings. What if I subtracted those? What if I took 100x minus x? Now, clearly, 100x minus a single x is just 99x. Okay, nobody doubts that. We already defined 100x, we already defined singular x. So 100x is 83.838383 and then minus 0.838383 That's a fancy term in math. It's actually an ellipsis, sorry. But, all right, how does that help us, guys?
Well, that's cheating.
It's cheating? How come?
No, I'm kidding.
It's not cheating, but it's sneaky, right? It's very sneaky. Okay, so how does that help us, guys? Because when we subtract that, we're left with what? 83, right? Because all those non-terminating decimals, but repeating, cancel out. So I'm left with 99x equals 83, or in other words, 83/99. And guys, isn't that an integer divided by an integer, which is the very definition of rational? Now, what if you don't believe me? What do? Yeah, stick it in the calculator, right? And of course, if you were to stick 83 over 99 in your calculator, it would be 0.83838383. It's our job just to show it's rational, okay?
So if we were to use this rule with a difference of 2 repeating numbers, it would always be that number over 99?
Correct, okay? If it was over 3 numbers, what would it be, guys? Not 1,000. 999.
999.
If it was 4 numbers, it would be over 9999, okay? In fact, by the way, how many of you guys have suffered through Calc 2 and done the geometric series of this? Okay, now you might not remember how to do it, right? But you remember doing it. And that's okay, I'm not asking you guys to do it.
Geometry says like 1 over x to the power p, right?
Yeah, that's how you would do it, and that's a geometric series, okay? So long as x is convergent to that series. All right, questions I can answer, guys. Everyone feel okay about this much? Okay, my suggestion would be, guys, go home and try to work through maybe the first 5 problems, okay? I think on assignment number 4, so that way you guys can kind of get used to this, and that way when you come in on Wednesday, you're not cold with this. All right, I do have your guys' examinations, so let me get those back to you guys. All right. Oh yeah, I'm sorry.